In the online lecture series for the B.Sc second year, we have to see the topic of the differentiation. In the first slides, we have to see the definition of a partial differential equation. The partial differential equation are those equations which contain the partial differential coefficient, independent variable and dependent variable. The independent variable will be denoted by x and y. The dependent variable will denoted by z. The partial differential coefficient are denoted as follow. That is, the dou z upon dou x is equal to p. Dou z upon dou y is equal to q. Dou square z upon dou x square is equal to r. Dou square z upon dou x dou y is equal to s, and dou square z upon dou square y is equal to t. The second definition of order. The partial differential equation is same as the order of the highest differential coefficient in it. Method of the forming partial differential equation. The first method is by eliminating arbitrary constant, and the second method is by eliminating arbitrary function. In the first method, the method of elimination arbitrary constant, the first example is partial differential equation form x square plus y square plus z minus c square is equal to a square. The solution form x square plus y square plus z minus c bracket square is equal to a square. That is the equation number first. Contains the two arbitrary constant a and c. Differentiating one partially, we have to get 2x plus 2 z minus c dou z upon dou x is equal to 0. Differentiating one partially, we have to get 2y plus 2 z minus c dou z upon dou y is equal to 0. Let's eliminate c from equation 2 and 3. From the 2, we have to get in bracket z minus c is equal to minus x upon p. Putting this value of 3, we have to get y is equal to minus x upon p, q is equal to 0. That is, yp minus xq is equal to 0. The method of elimination of arbitrary function. The example number 2, partial differential equation from z is equal to f of x square minus y square. The solution form z is equal to f of x square minus y square, that is the equation number first. Differentiating one with respect to x and y, p is equal to dou z upon dou x, that is f dash in bracket x square minus y square 2x, that is the equation number 2. Q is equal to dou z upon dou y is equal to f dash x square minus y square in bracket minus 2y, that is the equation number 3. Dividing equation number 2 by equation number 3, we have to get p upon q is equal to minus x upon y, or py is equal to minus qx. The second, the solution of equation by the direct integration. In this method, we have to see the first example, d cube z dou x square dou y is equal to cos of 2x plus 3y. The solution form dou square z dou x square dou y is equal to cos of 2x plus 3y. Integrating with respect to x, we have to get dou square z upon dou x dou y is equal to 1 upon 2 sine of 2x plus 3y plus f of y. Integrating, we have to get dou z upon dou y is equal to minus 1 by 4 cos of 2 plus 3y plus x. Integration of f of y dy plus g of y is equal to minus 1 by 4 cos of 2x plus 3y plus xy y plus g of y. Integrating with respect to y, we have to get z is equal to minus 1 by 12 sine of 2x plus 3y plus x. Integration of phi of y dy, integration of g of y dy, z is equal to 1 by 12 sine of 2x plus 3y xp plus phi 2y. The solving the second example, dou square z upon dou x dou y is equal to x square y. Here z x0 is equal to x square plus z1y is equal to cos of y. In the solution form, dou upon dou x, dou z, dou y is equal to x square y. Integrating with respect to x, we have to obtain dou z upon dou y is equal to x cube upon 3 plus y plus f of y. Integrating with respect to y, we have to obtain z is equal to x cube upon 3 into x square upon 2 plus integration of f of y dy plus g of x. Here we have to put f of y is equal to integration of d of y g of x. That is, the z is equal to x cube y square upon 6 f of y g of x. This is the equation number first. In the condition first, putting z is equal to x square and y is equal to 0 in 1, we have to get x square is equal to 0 and f of 0 plus g of x. Putting the value of g of x in 1, we have to get z is equal to x cube y square upon 6 plus f of y plus x minus f of 0. In the condition 2, z 1 upon y is equal to cos of y. Putting x is equal to 1 and z is equal to cos of y, in 2 we have to get cos of y is equal to y square upon 6 plus f of y plus 1 minus f of 0. Putting x is equal to 1 and z is equal to cos of y, in 2 we have to get cos of y is equal to y square 6 f of y plus 1 minus f of 0. Putting the value of f of y in 2, we obtain z is equal to 1 by 6 x cube y square plus cos of y minus 1 by 6 y square plus f of 0 plus x square minus f of 0. In the next slide, we have to show z is equal to minus 1 by 12 sine of 2x plus 3y plus x of phi of y dy plus g of y dy. Z is equal to minus 1 by 12 sine of 2x plus 3y xp plus phi of y. Next, solving the next problem, dou square z upon dou x dou y is equal to x square y. The subject to the condition z x0 is equal to x square, z1y is equal to cos of y. The solution form dou upon dou x dou z dou y is equal to x square y. Integrating with respect to x, we have to obtain dou z upon dou y is equal to x cube upon 3 y plus f of y. Integrating with respect to y, we obtain z is equal to x cube upon 3 plus x square upon 2 plus f of y dy plus g of x. Here f of y is equal to dy plus gx. Z is equal to x square y square upon 6 into f of y plus g of x. This is the equation number first. In the condition first, putting z is equal to x square and y is equal to 0. In 1, we have to get x square is equal to 0 plus f of 0 and g of x. Putting the value of g of x in 1, we have to get z is equal to x cube into y square upon 6 plus f of y plus x minus f of 0. This is the condition number 2. In the condition number 2, z of 1 y is equal to cos of y, putting x is equal to 1 and z is equal to cos of y into, we have to get cos of y is equal to y square upon 6 plus f of y plus 1 minus f of 0. Putting x is equal to 1 and z is equal to cos of y into, we have to get cos of y is equal to y square upon 6 f of y plus 1 minus f of 0. Putting the value of f of y into, we obtain z is equal to 1 by 6 x square plus y square plus cos of y minus 1 by 6 y square minus 1 plus f of 0 plus a square minus f of 0. In the next slide, we have to see dou x minus dou y upon x square minus y square plus ax is equal to dou y upon dou z upon y square minus a square, ax minus a square plus xy. Integrating the first two number of equation 2, we have to get log of x minus y is equal to log of y minus z plus log of c1. Log of x minus y upon y minus z is equal to log of c1, or x minus y upon y minus z is equal to c1. Similarly, from the last two member of the 2, we have y minus z upon z minus x is equal to c2. This is the required solution is f of x minus y, y minus z upon a minus x is equal to 0. Next, we have to see the method of the multipliers. Let auxiliary equation be the dou x upon p is equal to dou y upon q, dou z upon r. L, m, n may be the constant or the function of x, y, z. Then we have dou x upon p, dou y upon q, dou z upon r is equal to L dx plus m dy, n dz upon lp plus mq plus nr. L, m, n are the chosen in such a way that lp plus mq plus nr is equal to 0. L dx plus m dy, n dz is equal to 0. Solve the differential equation if the solution is u equal to c1. Similarly, choose another set of the multipliers L1, M1, N1, and if the second solution is B is equal to C2, this is the required solution of f of u, B is equal to 0. Solve. In the next slide, we have to solve the example mz minus my dou z upon dou x plus nx minus lz dou z upon dou y is equal to ly minus mx. In the next slide, the solution of the equation is mz minus my dou z dou x plus nx minus lz dou z dou y is equal to ly minus mx. Here in the auxiliary equation, dou x upon mz minus ny, dou y upon nx minus lz dou z ly minus mx. Using the multiplier x, y, z, we have to get each fraction x dx y dy plus z dz upon x mz minus ny plus y nx lz plus ly mx is equal to x dx plus y dy plus z dz upon 0. Therefore, x dx plus y dy z dz is equal to 0. Integration, we have to give x square plus y square plus z square is equal to c1. This is the equation number 1. Again, the multiplier wise, we get the L, m, n. Each fraction L dx plus m dy plus n dz. L, m, z minus ny plus m, nx minus lz plus n, ly minus al is equal to L dx plus m dy plus n dz is equal to 0. Therefore, L dx plus m dy plus n dy is equal to 0, which is give the integration equation Lx plus m dy plus n dy is equal to 0. Here we have to see methods of multipliers and methods of fraction by eliminating arbitrary constant and eliminating arbitrary function. In the next lecture, we have to see the example of that. Thank you.